Are we here? Okay. Uh, right. Good afternoon, everyone. Welcome to the lectures of the chemical process, elementary principles of the chemical processes. Right. Let me make it louder. Uh, so on on Monday, we talk about one condensable components in a multiple components gas liquid system, and this is an example. So we make an example. An example is that you have many type of gases like nitrogen, oxygen, carbon dioxide, and argon, for example. But you only have one condensable component, which is water. So you will create an environment like this. You have different pressure and temperature, and you have a lot of species in a gas phase. But only one type of gas can be condensed, and that which is H2O, right? So for the molar fraction, Yi, and vapor pressure of the components, you know that you have molar fractions of the gases in a gas phase, right? And then but only one fractions in liquid phase, which is Ya equal to 1, and A will be H2O, right? Okay, and then and then we introduce you Raoult's law, which is a limited case of the Raoult's law. That is only for single condensable species. So you know the Raoult's law is Yi type total pressure, which is capital P, equal to Xi. Xi is the molar fraction of the I species, right? In the liquid phase, and times Pi star function of T. Pi star function of T is that is the ice the partial the vapor pressure of the ice species at temperature T, right? So this is what we know about the Raoult's law. But because this is a special case, which is a single condensable species, so Xi will be equal to 1. So as a result, you will have this equation like Yi times capital P equal to Pi star function of T. Okay, so you need to learn this. And because Dalton's law, we know Pi will equal to Yi times capital P. Yi is what? Is a molar fraction in gas phase. Right, so the combination of the Raoult's law and the Dalton's law, you will be able to find out the molar fraction of the A species, B species, and C species, as well as the partial pressure of A species, B species, and C species, for example. So what you need to know is that molar fraction in gas phase and also partial pressure in gas phase. Okay, that's what you need to know. And after that, we introduce you if all the liquid vaporized, there's no liquid in this system. So the Pi will, and this reach to equilibrium. That means that there's no more change. So the Pi will always less than Pi star. So and this at this moment we call this is we call it superheated vapor. Superheated vapor is very important in the power station, right? Because we want to use the superheated vapor to be a source, an energy source, and push the turbine move. And if the turbine move, we can generate electricity. So you can use it. You can use electricity at home. This is the principle of the power station. Okay, so Pi was less than Pi star, and this is what we call superheated vapor. So if Pi equal to Pi star, then in that case we call saturated vapor, which is this case, right? And Pi less than Pi star, this is superheated vapor. So there is no water exists in this system. And there's no way to let you have Pi larger than the Pi star. If you want to attempt this condition, all the gas will become the gas introduced into this system will be condensed. No matter you change the temperature or pressure or what, Pi never be larger than the Pi star. Okay. So, and next topic today we are going to talk is evaporation and boiling. We have learned this before. So now let's use a more scientific way to describe what's the difference between vaporization and boiling. So before that, we understand vaporization is that the bubble cannot form since the vapor pressure is less than the atmospheric pressure. So the water molecules only vaporize from the surface only. So this is what we know in the before. Okay, how about boiling? So the bubble can be formed right since the vapor pressure can overcome atmospheric pressure. So the bubble will form inside the liquid water, and because of the pressure, it will go up. So not only the water molecule vaporize from the surface, but also the water molecule vaporize from the inside of the liquid water. Okay, this is what we know about evaporation and boiling. So how can we define evaporation better, or using a sign of scientific, using another way to describe? So the mechanism of the evaporation of a liquid depends on what? Relative value of the vapor pressure of the liquid and the total pressure. What does that mean? So we are talking about vapor pressure of the A species in a gas phase, which we will call PA star, right? PA star. Okay, and the total pressure, P. What's the relationship between total pressure and the PI star? Okay, so for the evaporation, the P star, this one, will be always less than P. So this is what we call the evaporation. Okay, so Pi star less than the total pressure, capital P. The process involves transfer the molecules from the surface of liquid to the gas above the surface. So at this moment, if the Pi star is less than the capital P, the water molecule will always or only vaporize from the surface only. Okay. However, so for example, if this condition is at 25 Celsius, okay, so if this condition, this system is at 25 Celsius, and if you check the table of the vapor pressure of the water in the table, you will realize the vapor pressure of this in this condition at 25 Celsius will be only 23.76 millimeter mercury. However, at the room temperature at 1 atmosphere, then the total pressure will be 760 millimeter mercury. So in this case, you will realize Pi, which is 23.76, is less than 760 millimeter mercury. At this moment, you understand this is the process of evaporation. Okay? However, if the water vapor, the pressure of the water vapor reach to 760, that means what? That means it's boiling. In this case, if you check the water vapor pressure from a table and the temperature at 100 Celsius, this partial pressure or water vapor pressure will be 760, and it's equal to the total pressure. And this time, all the water molecule inside this liquid will start to boil. Okay? So for the boiling point of the liquid, that means Pi star will be equal to capital P, total pressure. So the boiling point is that Pi star equal to P, the vapor bubble formed throughout the entire liquids, but predominantly at the heated containers walls. that is the liquid boils, right? So the temperature at which Pi star equal to P, capital P, is the boiling point of the liquid at a given pressure. Okay, this is the definition of boiling. So I want to summarize this for you to let you have a better picture. So when we talk about Pi less than Pi star, this is what we call evaporation. Remember this one, evaporation, right? Pi and P and capital P. If Pi star equal to P, that means what? Liquid boiling. However, if this Pi is less than Pi star, that means superheated. If Pi equal to Pi star, that means saturated. So you might say, well, Professor, how about Pi equal to Pi star and equal to capital P? That's boiling process and reach to the saturated vapor, right? Okay, so just give you a roughly idea about the relationship between Pi star, and the capital P. Okay? Use your imagination to think of this, the relationship between these three pressures. Okay? Right. So, next topic, we are going to talk about the humidity. You know, the humidity, you use this, you probably have this, this is what we call hygrometer. This is hygrometer, which we measure the humidity. This is called thermometer. Thermometer is to measure the temperature. So you might have these meters at home or in your dormitory. So you can know that now the temperature is high or low, and humidity is high or low. For example, these 2 days we have heavy shower outside, right? It's heavy rain, so the humidity will be very high, right? So you don't feel well because you feel your skin is sticky because with a lot of water cannot be vaporized. If the air is dry, the water can be vaporized very easily. So you feel cold, you feel better. So if you have high humidity in this environment, that means what? You don't feel well. Okay, so and this is another one. This is digital, right? This is digital. That means tell you the 24.5 Celsius, and the RH means relative humidity. R stand for relative, H stand for humidity, right? So you have smile. Smile means that good weather, right? And the humidity reached to 68. 68 is not good humidity. It's not good level of humidity. So you see the face is not happy face, right? Okay. So now, what we want to talk in this topic is that how are we going to determine the humidity? So this term is called saturation and humidity. Saturation refers to any gas vapor combination, but humidity only talk about like H2O. It's about air and the water only. So humidity refers especially to a air and water system. So saturation is this system. This is a general case. It can ABC can be water, carbon dioxide, air, high argon, for example. But if we are talking about humidity, the system change to air, water. Okay. Right. Okay. And this is a special case for only one condensable components in a liquid and gas phase. Right. And I'll go through this quick. So this is important, and you use this. You have this kind of meter at home. So we call relative saturation or relative humidity. So the definition of relative humidity is that this is the vapor pressure, right, of the water. Okay, and this is total pressure, and you have pressure of air, of course. So this is a definition of the relative pressure, relative humidity. I don't need to remember this equation, but I want you to know the definition of this equation. Because if I tell you the relative humidity is 60%, so can you tell me what's the total pressure, what's the partial pressure of the air, of the water in this environment? Okay, you should be able to tell me about this according to this equation. Okay, so SR stands for relative, right? So Pi divided by Pi star function of T times 100. So you understand Pi is partial pressure of the water vapor, of course, and this is saturated, right? Pi star is saturated at a function of T. You can check the you can check the table according to the different temperatures. Okay, so I give an example. A relative humidity 40. If I say that now this environment is 40 relative humidity, is this dry or is this very wet? According to your experience, if I tell you RH is 40, this environment is dry or wet? Dry, right? Dry. You feel comfortable between the 40 to 60 to 70, something like this. You don't feel well if it's too dry. If you go to the desert, it's too dry. If you go, if you have the weather like yesterday, you feel too wet, right? So relative humidity of 40, for example, signify that the partial pressure of the water vapor relative to 4 out of 10 of the water pressure of the water at vapor pressure of the water at the system temperature. So what does that mean? For example, if I say that, well, at this moment, the temperature is 25 Celsius. So you know this is 25. So you can check the table, what's the saturated vapor pressure of water at 25 Celsius. So you can find the answer here by a table, or you can use equations, or you can find it from the figures, for example. So you understand at 25, at water at 25 Celsius, the vapor pressure is 23.756 millimeter mercury. So you put this number here, right? And if this is 40, so you realize at this moment, the water pressure will be 9.5 millimeter mercury. Okay? Okay? And also, you know the fraction. If I tell you, well, please tell me the molar fraction of water in a gas phase. Can you tell me this? Yes, you can. Why? Because you use Dalton equation. You have a partial pressure and total pressure, right? Where's total pressure? 1 atm, for example. 1 atm. So you know the molar fraction of the water in a gas phase. Okay? So I feel this is very important, and this is related to your daily life. So please, if you ask a student in a mechanical engineering, they don't know how to do the calculation. But as you are a chemical engineer, or as you are a student from the chemical engineering department, you need to know how to do the calculation. Right. Okay. Another definition is molar saturation. I think it's just a difference between differences of the definition only. This is Pi divided by P, capital P minus Pi. What does that mean? This is what? This is the pressure, water pressure. This is what? Air pressure. That's it. Because P minus Pi means if you have only air and water, so of course this will be, excuse me, this will be the pressure of the air, pressure of the water and pressure of the air. So you might say, wow, why pressure of the air divided by pressure of water pressure and air pressure will be equal to more of water and more of the vapor-free gas, dry air? Why? PV equal to nRT, right? Because the volume is constant. So PV equal to nRT. N is what? More of the vapor. Okay, this is more of the water. More of the dry air. Okay, so there's no problem. So this is one, right? Okay. So this is more of the vapor divided by more of the air. And another definition is called absolute saturation. So the definition of absolute saturation is what? Just before we say more of the vapor divided by more of the dry air, right? And now this is the mass of the vapor divided by mass of the dry air. Why? Because this is PM, this is definition, right? PM and PM. So this is dry air, the partial pressure of the dry air, partial pressure of the water. I hope you still remember PM equal to what? PM equal to DRT. D stands for what? Density, right? So if the value is a constant, and then if you compare with a different density, that means you compare with what? The mass, right? You compare with the mass. So PM equal to DRT. So DI will be here, and D dry air will be here. But we are talking about the same area, same volume. So we are talking about the different mass. This is the mass of the vapor. This is the mass of the dry air. Okay, so this is the third one, absolute saturation. And another one is called percentage saturation. Percentage saturation is this. Okay, so this is another definition. This is saturation. This is the previous one, molar saturation. Oh, we put it here. Okay. So I don't want you to remember. This is an example. Just tell you that if I give you condition, I want you to find out this for the relative the definition of the humidity. And I don't want you to remember these equations. If in the future, if you want to find out this, you can just go and check the book or Google it. You will be able to find these equations. The only thing you need to know is why we need to use this, right? So first one, we use this every day, right? Relative saturation, relative humidity. And this is the ratio of the mole. Okay, this is molar saturation is ratio of the mole. This is the ratio of what? Ratio of the mass compared to the dry air, water and dry air. And another one is percentage of saturation. I think among these four equations, the most important equation I believe or I think is relative saturation. Okay, because RH is the one you see most of the time. So again, I want to let's move it to the next week before when we just have the review this. So this is called high. So how are we going to measure the humidity? Okay, this is called hygrometer. Hygrometer. You know, this hygrometer tell you that the temperature between like 15 to 25 is what? Is comfortable temperature, right? If you go up to 30, it's too hot. If you go down to 15, it's too cold. This is the temperature thermometer, right? Hygrometer is this one. The relative humidity between 40 to less than 70 is comfortable, but more than 70 is too wet. Less than 40 is too dry. You don't feel well between after 70 or before 40. So how are we going to measure the humidity? There are many types. There are two categories. The first one is called classic hygrometer. The second one is modern hygrometer. Okay, the modern one is you use capacitive, resistive, thermal, or gravimetric method to measure. I don't have time to talk about this. If you are interested in this kind of topic, you can Google it, or you can go to YouTube to find out. Okay, one of the interesting things is that, do you know hair can be used for hygrometer? Your hair can use for hygrometer. Why? Hygrometer means that the air tension will change because of humidity. If the hair tension changes because of humidity, you can use hair for the hygrometer. Okay. Right. Again, I don't just let you know this you can use hair to be a device, a component, I should say, to be a component for a hygrometer, or key, I should say, key component. Right. The last thing is that superheated vapor. Now there are many. The superheated vapor. I just give you an example. Is the power station, right? You use it in the power station. You can use this kind of superheat superheated or this kind of overheated vapor for cooking. Okay, you can make a nice meal, nice food using this machine, using this technique. Okay. Right. Any questions? No? Okay. So now let's go to section 6.4, multi-component gas liquid system. In the 6.3, we talk about multi-components, but only one condensable component. But section 6.4, we talk about many of the components can be condensed. So this case is, the case in the left-hand side is only water can be condensed, right? This is 6.3. The 6.4 is that many components can be condensed. Okay, and we want to know the molar fraction in gas phase and molar fraction in the liquid phase. Okay, so at this moment, in the section 6.43, we are dealing with the molar fraction in gas phase only, because the molar fraction in the liquid phase is always equal, is always 1. But now the molar fraction in the liquid phase is not only 1, is not 1. So this is what we call vapor liquid equilibrium, VLE data, VLE. You reach the liquid and vapors, these two systems reach equilibrium. So at this moment, we can tune the different pressure and different temperature. And you want to know that, we want to know the molar fraction in the gas phase and also molar fraction in liquid phase for all the components. So the best way, how can we determine this molar fraction? The best way to evaluate equilibrium components is from the tabulated data. So if you have a data for this system, you just check the data, check from the table, and you get the answer. That's easy. According to, you have different pressure and different temperature. And you understand this data is from is from many scientists or engineers who did a lot of experiments and they get this data, right? So you can find this kind of data in Paris Chemical Engineering handbooks. This is our Bible, remember? Okay, for chemical engineers. Okay, so important thing is to find the partial pressures of the vapor over various liquid solution. I'm going to show you an example. This is one example. This system has air, sulfur dioxide, and water. And you have different pressure. At this system, you can have different pressure and temperature. So you will have different molar fraction in gas phase, and you will also have different molar fractions in the liquid phase. And this is the table showing you here. And you might say, why, Professor, what is this example? Air, is this system exist? Air, sulfur dioxide, and water. Is this system exist? Remember, we already talked about this before, this system. And there's an instrument which is dealing with this system, dealing with this process. Can anybody tell me what is this system? What is the name of that equipment? Anybody want to tell me? No? Air, sulfur dioxide, and water. There's a machine can dealing with this system. What is this machine called? Yes. Anybody 0.5? No? 1? No? 1 point? Yes. Yes. 可是你要告诉我名字啊，想不起来啊，嘿。Thank you very much. Scrubber, right? Because you have water and then sulfur dioxide gas, and then what? And you have sulfur dioxide, and the air come out, right? Come out, and you have water shower, spray water shower, and then water droplet will touch the sulfur dioxide, and because sulfur dioxide will dissolve in the water, so it becomes what? Sulfur SO3, right? SO3 and again with water become H2SO3, H2SO3, right? Okay. SO4, sorry, I'm sorry. Okay, so this is called scrubber. Okay, so this scrubber, this is the process of scrubber. So when you have a machine or when you have an instrument of a scrubber, and what you need is this table, because you want to operate this scrubber with different temperature, and if you know the composition of the sulfur dioxide in the air, so you can do the calculation. You need to know how many air you need, or what's the concentration of the sulfur dioxide in the liquid phase, and as well as in the solid phase. Okay. So let's do a little bit practice. Partial pressure of the water and sulfur dioxide. So we have different in this system. We have different pressure and temperature. And let's think, if you want to duplicate this, system, or if you want to create this system, how many information we need? Here we have 1, 2, 3, 4, 5. We have 5 unknowns. But how many information we need in order to get these 5 and to get these answers? Okay, let's use the degree of freedom analysis. This is what Gibbs rule, right? So 2C pi 2 plus C. How many components? 1, 2, 3, right? So you have 3 because air, water, and sulfur dioxide. So you have 3. How many phases? 2 phases. So minus 2. So equal to 3. What does this mean? This means that among these 5 unknowns, as long as you know 2 out of these 5, okay, as long as you know the 2 out of these 5 unknowns, then you can get another 3 answer. You can get another 3. Okay, so in this case, which is easy, if you have a pressure and temperature, then YH2O, YSO2, and XSO2 will be fixed. The value will be fixed. This is a table showing you the molar fraction is fixed in gas and liquid system. Okay, so how can we determine if this is, for example, this table is for 1 atm only. It's not for 2 or 0.5. No, this table is only for 1 atm only. So pressure is fixed, and up here is the temperature. Okay, from 10, 20, 30, 40 to 120, 130. And what is this? The gram SO2 per 100 gram water. So what does this mean? This means what? Molar fraction in water is fixed, right? So for example, if we know the pressure, this pressure 1 atm, right? And we know the temperature is here. So we fix temperature. And then, so this is fixed. So it's from unknown to known because I give you the pressure and temperature. Okay? Right. And then the fraction of A and B in the liquid phase, XA and XB, which is here. So this is 1 gram of the SO2 per 100 gram water. So if you know mass, of course you know the fraction. Through what? Molecular weight, right? Okay, so you know the molar fraction. So if I tell this, for example, uh, 3.0, and then 20 Celsius. You know 3.0, 20 Celsius will be the water molar. This is pressure. This is unit pressure, 17.3 and 191. Okay, so for example, if I give you 5.5 and 10 Celsius, the partial pressure of the water in gas phase will be 9 millimeter mercury, right? And then sulfur dioxide will be 247 millimeter mercury. So you will immediately realize the partial pressure of A and B, right? So here is that partial pressure of A and B. You might say, well, Professor, I still don't know. If I know the partial pressure, I still don't know the molar fraction of the A and B in the gas phase. Of course you know. Why? Dalton's law, right? Because you know the partial pressure and you know the total pressure. And the partial pressure times molar fraction equal to total pressure. This is Dalton's law. Okay? So please, this is an example showing you that. So originally you have 5 unknowns in this system. And if you know the temperature and the pressure, and with this table, you'll be able to find out another 3 unknowns. Okay? Next, this is what we call squabble. This is the example I just showed you, right? Squabble. So absorption of the SO2. So absorption means what? Shiso, right? Shisota. That's why we call shisota. Okay. I don't have time to read the text with you, but what I want to tell you is that this is the input equal. This is a process of input equal to output. There's nothing involved chemical reaction. So you have SO2 and air going to this scrubber, which is the dirty air, right? Dirty air. And you want to make it cleaner. You want to make air cleaner, so you need to have a scrubber. You need to have an air shower to have direct contact with this dirty air. So the liquid phase is that you have clean air, water in. So the shower come in, and then you dirty air goes up, clean water goes down, right? And then what you expect is you have dirty water, right? And then clean air. So liquid phase come out, and then you have SO2 and H2O because this dissolve. There's no involve any chemical reactions. So this is H2O, SO2. This is H2O. Sorry, SO2 and SO2 and H2O, right? Okay, and then you will have vapor phase. So you might have a little bit SO2. It depends on how good is this machine, right? How good is this scrubber? So SO2 might reach to 0, for example. But if this is not good, you might release some of the SO2 in the gas phase. But in this case, you have some SO2 here, and you have air, and you have H2O. Okay? And then we use a basis in the vapor phase in the input first. So it's 100 pound mole per hour. And then we know that the combination of the concentration of SO2, the components or the molar fraction is 40% of the SO2 and 50% of the air. We know that. The unit is pound per mole, right? Okay, this is what we know from the example 6.4-1. And what we also know is that in the water, this dirty water, we can have a sensor. We can do a detection. We realize this water has the molar fraction, non-molar fraction is 2 pounds of the SO. This 100 pounds of the water will dissolve 2 pounds of the 2-pound mass of the SO2. So this is the relationship between the water and the SO2. Okay. So of course we know that the molar fraction if we want to know. So and then the text tells us that in the example 6.4-1 tells us that this system reached to equilibrium at 30 Celsius and 1 atm. So 1 atm is at ambient pressure, and 30 Celsius is what? At room temperature, right? Something like this. Okay, so you have, and then now you might think that how many water you need to fit in this system. Okay, this is first one unknown. Of course, you don't have molar fraction because the molar fraction is equal to 1 because you have this is pure water. And then what you don't know, another one is that you don't know how many mass or how many moles of the in a come out from the as a clean air, right? Clean air. So, and also something you don't know is that the molar fraction of the air, water, and SO2. But here you only have 2 variable unknowns because another one you will notice because this one plus this one plus this one will equal to 1. So you only have 2 unknowns, which I mark in red color, right? I always mark unknown as a red color. So please remember this. So this is another one. It's NL2, which is you want to know how many moles come out in the liquid phase. And this is the molar fraction. And this is the ratio of the SO2 and H2O. But according to this, you'll be able to find out this, right? Why? Let me show you. So in this case, you have 1, 2, 3, 4, 5. You have 5 unknowns in this system. 1, 2, 3, 4, 5. So again, you have 1, 2. Let me see. Again, I just told you that this is the 1 atm, right? 1 atm table. So equilibrium at 30 and 1 atm. So this is a 1 atm table, and 30 is here. 30 is here. And you also know that information tells us that 2 pounds, 100 pounds of the H2O, there is a 2 pounds mass SO2. So this is 100 gram water. How many grams of SO2? You might say, well, Professor, this is pound, this is gram. This is the matter of the ratio, right? So it doesn't matter it's pound mass or it doesn't matter it's gram or kilogram, for example. It's the same because this is a matter of the ratio. Ratio will be all the same. No matter you talk about pound mass or kilograms or grams. Okay, so 2 out of 100. So 2 out of 100 is here. So you know that 30 here and 2 out of 100 here. So what you know is that the vapor pressure of the water will be 30.1.6, right? 31.16, 30, right? And then 31.6 and 176. So you know the partial pressure of the water is 31.6, and the H2O will be 176, right? Okay, 31.6 and then 176. So how are you going to get this? So because you know this, right? You know this, and so you know the molar fraction here in liquid phase. 1 out of 2, 2 out of 100, and you can get a molar fraction due to through what? Molecular weight. And what you don't know is these two. But you already know the partial pressure of the water is 31.6. The partial pressure of SO2 in the gas phase is 176. So again, you just use Dalton's law to get these two. So you can change the color from red to green. That means unknown become known. You get a value. Right? Okay. So this is the kind of calculation. I don't want to go through it with you because Once you know these two, then you only have three unknowns, right? And three unknowns use mass balance. Input, air input equal to output. Sulfur dioxide input equal to output, and water input equal to output. So you can get an answer. So you can solve out these five unknowns. The only key is what? You have this table. This table is what we call specification. You can get the answer of the YI, YH2O, and YH2O. Okay? Sorry, this is SO2. I'm sorry, SO2. Okay. So the notice for you to be careful is that this is pound mass. In gas, we always use moles, but in liquid, we always use mass. So you need to know how to do the conversion. That's the key. Otherwise, I think this is not a difficult example. Okay, so the next topic, which is I believe is a very important topic, is called Raoult's law and Henry's law. But before we go to this topic, let's refresh ourselves. Time for Kahoot. Right? This I think probably we cannot play Kahoot today. I don't know how to go from here. Today the title of Kahoot is vapor pressure. Let me I'm sorry that I think I probably go to this first. 已经简单的告诉你们一些，看到图了吗？卡户有些问题，请下来。进来教室。Right. I'm calling the TA now because I don't know how to. 下课啊。考务有些问题，可不可以请你下一下呢？或是请阿庆哦，好，拜拜。Right. 已经泄题了，对不对？刚刚有注意到吗？没有。好 ，Anyway， 没有关系，我们先介绍一下这个 6.4b Raoult's law and Henry's law. Again, this is phase equilibrium thermodynamics. We always talking about thermodynamics. What does that mean, thermodynamic? Everything reach equilibrium. It doesn't change. The situation doesn't change anymore. So it means that it means what? It's nothing to do with time, no matter now or forever. So it reached to equilibrium. The system doesn't change. Okay, that's what we call thermodynamic. And then if a system doesn't change with time, and the variable doesn't change with time, everything is fixed, and we want to know the value. We want to know why is this. Okay? So if apply give phase rule to a multiple component gas liquid system at equilibrium, you will discover that the composition of the two phases at a given temperature and pressure are not independent. Right. Okay. So the relations, we already talked about this, right? So because we want to know that the compositions, important things, what happened, can we do the calculations apart from, because you know that the previous example given us a table. What happens if you don't have table? Okay. If you don't have table, you need to find equation, right? Or you need to find some relationship between the gas and liquid. Okay. And in the previous section, like on Monday, we talk about what? We talk about Raoult's law, right? So that's related with the gas and liquid system. So this is important. So now we want to introduce you another law called Henry's law. The two simple expression in a gas liquid system in equilibrium is that Raoult's law is, we already learned this, right? Pi equal to almost, right? Pi times capital P equal to Xi Pi star. And Henry's law is that Pi equal to Pi capital P equal to Xi and then Hi function of T. So what is Hi function of T? This is Henry's law. Okay, so you already know Raoult's law. And now we want to introduce you another law called Henry's law. So Raoult's law is that this one, and you know this, right? We already introduced this to you. So now is Xi, you know, you need to know it's not equal to 1 anymore because this is not only one condensable system. And Raoult's law is that Raoult's law is an explanation of is generally valid when Xi is close to 1. Liquid is almost pure. What does it mean? This you have, for example, you have 3, 4, 5 species. And then if there's only one condensable component, which is H2O, then of course Xi will always close to 1. So now you understand this is this kind of species always easy to condense. That's why we need to use Raoult's law. I'm going to show you another opposite example. For example, water is always easy to be condensed. That will be the same as what? That will be the same as acetone. That will be the same as ethanol. Okay? So if you have a system like this, then you can use Raoult's law. So it's always also sometimes valid for over the entire range of the composition over for mixtures of similar substance, such as paraffinic hydrocarbons or similar molecular weight. It's telling you that Raoult's law is not only applied for the Xa is close to 1, but also applied for the similar substance. Okay? But this is another case. We are not going to talk about this more. So for example, is this toluene and benzene. These are very similar molecules. Okay? So they can use Raoult's law for this system. How about Henry's law? Henry's law is that, excuse me, Henry's law is that this is Henry's constant at temperature T. You know that this is Henry constant function of T. So what you need to know is that find this constant according to different temperatures. So you can have species, different type of species. So Henry's law, this is that Henry's law is generally valid for solutions in which Xa is close to 0, what does this mean, close to 0? Just now we talk about Raoult's law is always close to 1, right? And now this one is the Henry's law is xi close to 0. What does that mean? Close to 0 means what? It's dilute solution of A provides that A does not dissociate, ionize, or react in the liquid phase. What does that mean? That means the molecules applied for Henry's law normally is not easy to condense, such as helium, ethylene, carbon dioxide. This kind of is not easy to be condensed or dissolved in the water or dissolved in the gas in the become the liquid phase. Okay, so this we can use this to apply Henry's law. So the law is often applied to the solutions of the non-condensable gases. So now you realize Henry's law is applied for the species which is easy to condense and almost close to 1, xi almost close to 1. But Henry's law is for the gases which is not easy to be condensed. Okay, so the values of the Henry's law constants, you can find this in the Paris Engineering Handbook. Okay, I show you some examples, Henry's constant. So this is ethylene, C2H2. And this is the temperature. We use Celsius, right? 0, 5, 10, 15 to 30. And this is the Henry's constant here. And 10 power minus 3 times HA equal to this number. So what does this mean? This means if we have 20 Celsius, the 10 power minus 3 times Henry's constant at 20 equal to what? 1.21 atm. So Henry's constant will be what? Will be 1.21 times what? 10 to power 3. Okay, so you had to put this 1.21 times 10 power 3 in this place for this equation. Okay? Okay, so this is example of the ethylene. And this is example of air. This is ethylene. This is ethylene. Okay, this is helium, hydrogen, and hydrogen. Okay? So in your final exam, if I give you this table, and you need to know how to get the Henry's constant. Okay. Remember this unit here, 1.21 or 1.33, the unit is atm. And the temperature of the unit is Celsius in this case. Okay? Don't be confused. You might say, well, Professor, when I was a high school student, I don't learn this as a Henry's law. I learned Henry's law like this. Right? I don't know you learn this or not. Okay, this is different type of Henry's law, but anyway, we are talking about the same thing. But just want to let you know that the Henry's law we use is the one in the previous page, this one, in our lecture. Okay? So don't mix up with the one you learned in the high school. It doesn't help you to solve the problem in this class. Right. So this is a new term I want to introduce this to you. It's called ideal solution. So you have heard a term called ideal gas. Have you heard a term called ideal solution? What's ideal solution? This is a system, a gas-liquid system in which the vapor-liquid equilibrium relationship for every volatile species is either Raoult's law or Henry's law is said to inhibit ideal solution behavior. So you know that when we talk about ideal gas, we know that there's no interaction between molecules, and then there's no energy exchange, right? Between the wall and the molecules, right? So this is the ideal gas. So what happened to ideal solution? Ideal solution is that all the species in this system either apply Raoult's law or Henry's law. If this system fit this Raoult's law or Henry's law, this system will be called ideal solution. Let me show you an example very soon, okay? So ideal solution is that one for the Raoult's law or Henry's law is obeyed for all the components. So let me, okay, I have example next page. For example, like this. The system is like this: nitrogen, helium, oxygen, oxygen, and water. So if this, I told you, if this system is the ideal solution, then which equation you want to use for nitrogen? Which one? Henry's law, right? Because nitrogen is very difficult to condense under a very limited, not very high pressure or not very low temperature. So helium, which law you want to apply for helium? Henry's law, right? Because again, it's not easy to be condensed. Oxygen, Henry's law. Oxygen, Henry's law. Water, which one? Raoult's law, right? Because Raoult's law, water is easy to condense, and you need to use Raoult's law for the water in this system. If these 5 species can apply either Raoult's law or Henry's law, this system will be called ideal solution. Okay? So ideal solution in chemistry, an ideal solution or ideal mixture is a solution with the thermodynamic properties analogous to the rules of a mixture of ideal gases. So ideal gases is very close, but important thing is that with the important differences is the intermolecular interactions in liquid are strong and cannot simply be neglected as they can for ideal gases. That means what? Ideal gases in the the molecular interaction can be neglected, right? But in a liquid, it's impossible to neglect this interaction. But however, this can be regarded as an ideal solution. So the mean strength of the interactions are the same between all the molecules of the solutions. Instead of, you cannot neglect, but you can regard the interaction will be all the same for all the molecules. Okay? So the mixture obey value additivity. Okay? You can add the value. For example, 1 plus 1 equal to 2. Somehow it's impossible, right? So the entropy means what? Entropy means the heat of the mixing. So there's no energy exchange. Okay, so entropy is 0. Okay, these are 2 conditions or two examples that the value additivity, you obey the value additivity and the entropy is 0, or one of which Raoult's law or Henry's law is obeyed for all the components. Okay, so example 6.4-2 is Raoult's law and Henry's law. So the condition 1 here is that you have a mixture of the C2H6 and H2O, and at 20 Celsius and 2 atm. So they tell you that in gas phase you have 1 mole. You have 1 mole C2H6. So that means what? If I tell you have 1 mole of the C2H2 in the gas phase, so that means in the beginning you have 2 unknowns here, but if you know this, you will know immediately the molar fractions in gas phase. Okay? And then once you know the pressure and temperature, of course you know the molar fraction here. So how can you get this answer? So hydrocarbons normally are relatively insoluble in water. So the solution of the ethylene is probably extremely dilute. So that means Xi will be very, very small. So once I told you that C2H6 cannot be dissolved, and it will be the number is very, very small. So which law you should apply? Henry's law or Raoult's law? Henry's law, right? Henry's law. So use Henry's law, but when you get a Henry's law, you know Yi, right? You know Yi because of this. You know P, capital P, you know the total pressure, which is 20 atm. You don't know XA, which you need to find out actually. You need to find out XA. And what you need to get number is what? Henry's constant for C2F6. So this is C2F, the table for C2F6. Please tell me where is if you have pressure 20 atm is here, right? And so what you can get is this. Henry's constant is 2.63. Oh, sorry, I'm sorry. It's 20 Celsius. Okay. So you can put the answer here into this place, and then you get here. You get the answer. Right. I don't want to waste your time. So the answer you get is 7.6 times 10 to minus 6, which is very low. Okay. So and you found the answer. So the question 2 here is that another condition is that you have 50, 50. This is C6H6, and then which is benzene, right? This is 2M, 50, 50. So you have this system here. You know that this is liquid, right? So you know the molar composition of the XC6H6 and XC7H8. So according to this, you know this one. And you add 30 Celsius, which is, you know the temperature. So that you know this, and you know the temperature. So what you don't know is that pressure and the molar fraction in gas phase. And of course, if you know one of these, you will know another one, because these two get together will become one. So benzene and the toluene are structurally similar compounds, so apply Raoult's law. So this system can apply Raoult's law, as I just told you before in the previous 10 minutes ago, for example, probably 10 minutes ago. So use this, and you check the table, and you find this. So in order to check this, in order to get the vapor pressure, you can use Anthony's equation, or you can find the Koch's chart. You can use another equation if you want, but it will be easier for you to use Anthony's equation. So you get this answer, you get this number, and you don't know total pressure, but you know the fraction. You know this one, right? You know this one. So you know this, okay? And then you know this. Total pressure is what? These two parts together will be total pressure. Okay, so I think I want you to do this, practice this by yourself. So Anthony equation here, you need to find out this, and then you use Anthony equation to get the vapor pressure. Okay, so so the summary is that Raoult's law is for liquid normally it can be easy to condense or similar compounds, right? And important thing is you need to get the vapor pressure through the equation or table or chart. The Henry's law, you need to get a Henry's constant through the tables, and normally used for insoluble gas for Henry's law. For the liquid or similar components, use Raoult's law. Okay. Right. I think we run out of time to introduce you 6.4c LOSV calculations for solutions that obey Raoult's law. This is important. I think this might be in your final exam. So I want to leave this topic for next week. So please pay your attention for the next week to the lectures, for the lectures next week, okay? Right, okay.